Welcome to Lesson 4 of Applied Physics. This lesson covers vectors. Many of the quantities used in physics have a direction associated with them. Such quantities, which are not completely specified unless a direction and a unit are indicated as well as a numerical value, are known as vector quantities. In this lesson you will cover the following objectives. Know the difference between a scalar and a vector quantity, and understand the fundamental concepts behind vectors representing mechanical quantities. Before moving on, try solving the following problems. If you are successful, you probably don't need to continue the lesson. If not, please continue to learn about vectors. Consider this example. If you move a coffee cup along a table 10 centimeters to the east and then 10 centimeters to the north, you will have displaced your cup 14.1 centimeters to the northeast. That is, the final position of the coffee cup is 14.1 centimeters to the northeast of where it started. The displacement is a vector quantity. However, if you look at the distance the cup traveled, you note that the coffee cup will have traveled a total distance of 20 centimeters. This distance does not have direction associated with it, only magnitude. Such a physical quantity is called a scalar quantity. A scalar quantity is completely specified by a number and its proper dimensional unit. Before moving on, try solving the following problems. If you are successful, you probably don't need to continue the lesson. If not, please continue to learn about vectors. Consider this example. When writing the symbol for a vector quantity, an arrow is added over the chosen symbol to indicate the vector nature of the quantity. For example, the vector A would be symbolized by an A with an arrow above it. If you are only concerned about the magnitude of the quantity and not its direction, you use the same symbol without the arrow. A quantity, such as displacement, that is only completely determined when you have given both its magnitude and its direction is called a vector quantity. A vector quantity can be represented graphically by an arrow in which the shaft of the arrow represents the line of action, and the arrowhead is the direction of action along the line. Such a representation is called a vector representation or vector. The length of the line gives the magnitude of the vector. Thus, a displacement of 8 kilometers northeast is represented by a vector 8 units long making an angle of 45 degrees to the easterly direction. The addition of distances or scalars follows the usual rules of addition. The addition of displacements or vectors must take into account the directions of the displacements involved. In this example, the first displacement, from your home to the physics building, and the second displacement, from the physics building to your home, are in opposite directions. The addition of these two vector displacements gives a zero net displacement. You ended up where you started. Suppose you ride a bicycle from your home to the physics building, a straight line distance of 2 kilometers. The total distance you traveled was 2 kilometers. After you ride back home, you will have traveled the distance of 4 kilometers, but your net displacement is 0. If you start and stop at the same spot, you have 0 displacement. Displacement is a change of position, including the directional change. Distance is the actual length of the path that you covered, and the angle doesn't matter. Vectors do not obey the simple algebraic properties of scalars. For example, when you add the two scalars, 2 plus 2, you obtain 4. If you add two vectors, both of magnitude 3, you may obtain any number from 0 to 6 for the magnitude of the sum of these two vectors. You must add these vectors using the tip-to-tail method, and you must consider where you started and where you stopped. You must include the direction you traveled. As an example of how to add vector quantities, imagine that you rolled a marble 10 meters across the floor in a direction 37 degrees north of east. The marble then struck a wall and rolled back 8 meters in a direction 30 degrees west of north. What is the resultant displacement of the marble? The next page will give you a better mathematical breakdown of this problem. To see how a graphical method can be used to add vectors, refer to this figure. We represent the first displacement by a vector pointing 37 degrees north of east, scaled to represent 10 meters in length. The vector is labeled A in the diagram. The second displacement of the marble, represented by vector B in the diagram, is drawn in a similar manner. To add vectors A and B, we draw B extending from the tip of A. This method of vector addition is known as the tip-to-tail method. On your own, draw the vector R and label it as the resultant. The length of this vector represents the magnitude of the addition of the two vector quantities, and a measurement of the angle is its direction. Applied physics students can do this type of activity by using a ruler, grid paper, and a compass. You can do this without knowing how to calculate using trigonometry if you need to. Be sure to draw these problems to scale. If you get out your grid or graph paper and you read the problem statement that vector A and vector B are added together, you can scale the problem and draw it into a triangle. And using a protractor and a ruler, you can calculate the resultant of adding the two vectors together. Forces add this way, so do displacements, velocity, and acceleration vectors. Now suppose you wish to add a third vector C to the A and B, as given in the previous example. Vector C has a magnitude of 6 meters and points out due west. Vectors A and B are drawn tip to tail to B. All three vectors are now joined tip to tail on the diagram. We can view the new resultant, the vector sum of A plus B plus C, by drawing a vector from the initial point of A, the tail of A, to the tip of C. As before, the magnitude of R is obtained by measuring the length of R on the diagram and applying the scaling factor. The direction of R is obtained by measuring the angle to the east-west axis with a protractor. These two measurements provide all the data needed to define the vector R in terms of its magnitude and direction. From the diagram, we obtain the magnitude of R as 13.1 and the direction as 81 degrees north of west. The same procedure can be applied to any number of vectors. Previously, you were asked how you might add two displacements, each of 3 kilometers magnitude, to obtain a final displacement of 3 kilometers. From this graphical method of adding vectors, you see that the resultant R and the two vectors A and B form a triangle. If A, B, and R each have a length 3, then A, B, and R must form an equilateral triangle. This means that B must make an angle of 60 degrees with A, and R will make an angle of 60 degrees with B. You can find the difference between two vectors by using the same basic procedure. To find the value of the resultant vector when vector B is subtracted from vector A minus B, you add the vector, negative B, to the vector A, and follow the same procedure as was used for adding vectors. The vector negative b is a vector that has the same magnitude as vector b, but it is in the opposite direction. Using the same vectors a and b as in the previous examples, the graphical subtraction of b from a is illustrated here. In this example of vector subtraction, r is about 7 degrees south of east with a magnitude of 12 meters. It is not always convenient to graphically add vectors, and, as with any graphical method, it is only as accurate as the person doing the scaling and drawing. A more accurate result is obtained by using a method based on trigonometry. This method is called a component method and is based on the fact that for any vector, a right triangle can be formed when placing the vector at the origin of a Cartesian coordinate system. Consider again A from the previous examples. When drawn on the Cartesian coordinate system, the vector makes an angle of 37 degrees to the positive x-axis. Remember, if we keep everything on a classic grid system, that we can add or subtract anything in the x direction. and anything in the y direction. When you do this, you end up with a net value in the x direction and a net value in the y direction. With these values, you have a single simple triangle which you can draw out and measure the resultant, or you can use trigonometry to solve for the hypotenuse of the triangle. If a line is drawn straight down from the tip of A perpendicular to the x-axis, the length of that line is the amount of the vector that is in the y direction. That is, it is the projection of the vector in the y direction. We call this the y component of A, designated AY. The line drawn from the tip of A goes to a point on the x-axis. The distance from the origin to the point where the vertical line intersects the x-axis is the amount of the vector that is in the x direction. That is, it is the projection of the vector in the x direction. We call this the x component of A, designated AX. The vector A and its components form a right triangle, so the basic trigonometric relationships of sine, cosine, and tangent will apply to the triangle. From the diagram, we note that the x component of A is the side adjacent the angle that A makes with the x-axis, and that the length or magnitude of A forms the hypotenuse of the triangle. From trigonometry, we know that the cosine of an angle is defined as the side adjacent the angle divided by the hypotenuse, or in this case, the x component divided by the magnitude of A. This method finds the x component of A. The same concept can be applied to find the y component of A, this time using the definition of the sine of an angle as the side opposite the angle divided by the hypotenuse. Any vector can be written in terms of its components. When adding two or more vectors, the components of the resultant vector are given by the algebraic sum of the corresponding components. In other words, the x component of the resultant is determined by the sum of the x components of all the vectors being added together. As an example of how it works, we'll go back to the previous example of adding together A and B. The vector A was 10 meters at an angle of 37 degrees to the positive x-axis, and B was 8 meters at an angle of 120 degrees from the positive x-axis. The first step in applying the component method is to draw a sketch showing both vectors on the coordinate system. This page is significant to the understanding of how we will add vectors in component form algebraically. You should memorize this basic format, as we will fill in this chart nearly every time when we work on force-related problems. Information is also on the following chart as well. The next step is to determine the components of the vectors. This is summarized in this table. The components of the resultant vector are found by summing the respective components of the individual vectors as seen in the table. Once the components of R are known, the resultant can be sketched on a coordinate system. Since both components are positive, R is in the first quadrant of the coordinate system. The magnitude of R is found using the Pythagorean theorem, where the two components are the legs of the triangle and the magnitude of the vector is in the hypotenuse. The direction of R is found by using the definition of the tangent of the angle. The two components of R are the sides opposite and adjacent the angle that R makes to the x-axis. Since the tangent is defined as the side opposite divided by the side adjacent and both sides are known, the inverse tangent can be used to find the angle. Using the Pythagorean theorem and the equation for the inverse tangent will always be the fundamental basis for finding the resultant's magnitude and direction.